Okay, so back to the problem we left off on was this nitrate ion or this nitrogen trihydride. So we just finished adding 8 electrons to each atom in the molecule, so they're fulfilling the octet rule. So everyone's got their 8. And now the last step would be, let's make sure the electrons in our picture match those over here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. Okay, so this is the first example of the electrons in our picture not matching the number we have available. So this would not be possible. So at this point, we need to look back up at the instructions. Now, if there are too many electrons in the picture, we're going to add bonds to the central atom. And as we said in class, when you add a double bond, you are going to erase 2 alone pairs, one from each side of the bond, because the bond will take care of more of the shared electrons now. It doesn't matter where we add this double bond, because we're going to think of the concept of resonance. When a double bond could exist in 2 places, it's actually flipping between all these places. So it doesn't matter where we put it. I'm just going to put it on the left side, and look at what I do. Double bond, erase, erase. Now, why did I erase those lone pairs of electrons? So just count with me here. 2, 4, 6, 8. We don't need those electrons there to fulfill the octet rule anymore. They actually don't exist there. So now let's check the octet rule again. 2, 4, 6, 8. This oxygen's all set. This oxygen, 2, 4, 6, 8. That one's all good. This oxygen on the right, 2, 4, 6, 8. All good. Now the nitrogen in the middle. A double bond accounts for 4 shared electrons. So we have 4, 6, 8. Everyone's happy. Everyone's fulfilling the octet rule now. And let's just do one quick double check to make sure this picture electrons matches the number we accounted for. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now this is the Lewis structure for the nitrogen trihydride or the nitrate ion, and technically we should put this whole thing in brackets and put a little negative sign out there to remind ourselves that this is an ion and not that this is a polyatomic ion and not just a straight up molecule. Okay, let's try another one. We have the CO3 2 minus, carbon 4 valence electrons, oxygens 6 each times 3, and then this is a negative 2 ion, so let's make sure we add 2 there. So we have 24 again for this molecule. It's kind of similar to that last one. Let's get carbon in the middle. Let's get the oxygens on 3 sides. Let's start with single bonds. Let's fulfill the octet rule. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Okay, now we're fulfilling the octet rule. Now let's see if the electrons in our picture match those available for bonding. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. There are too many electrons in our picture again. So when there's too many electrons in the picture, we're going to get to examples where there's too few also, but this is where we're going to do the old double bond, erase, erase. Where do I want to add it? I don't know. How about here this time? Double bond, erase, erase. Let's see if the number in our pictures now match. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now we're good. Okay, the last example here, and the practice one, is carbon dioxide. Carbon has 4 valence. The electrons have 6 each times 2. So we have 16 electrons available for bonding in this molecule. Let's get carbon in the middle. Let's get the oxygens on both sides. Let's start with single bonds. Let's fulfill the octet. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Now let's see if the electrons in the picture match those available. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. This one are actually 4 too many. Let's just start out with a double bond somewhere. Let's go double bond, erase, erase. I would say always start out simple. So let's just see if this took care of things. 2, 4, 6, 8, 10, 12, 14, 16, 18. Still too many. If there's still too many, we need to add a bond somewhere. Now, this is kind of another example of resonance, but I would say rather than, we could add a triple here, I would say maybe add a double to the other side, kind of spread them out. Double bond, erase, erase. Now check out the carbon. It is still fulfilling the octet rule because it has 2, 4, 6, 8 electrons in its outer shell being shared. Let's count the total now. 2, 4, 6, 8, 10, 12, 14, 16. That's it. This is the Lewis structure for a carbon dioxide molecule. Okay, now I got time for a couple more examples, and I want to kind of focus on some of the different ones. Let's try this BrF5, this bromine pentafluoride. Now, bromine has 7 valence electrons. Fluorine's got 7 times 5. So we end up with 42 in this molecule. Let's put the bromine in the middle. Now, we can't put fluorines on 4 sides because there's 5 of them. So we just need to kind of spread them out equally around there. This is one little difference. Maybe kind of like that. Okay, let's still start with single bonds. Already you can see that the bromine is not fulfilling the octet rule, or it's maybe an exception to that octet rule, and that's okay because bromine is one of those atoms that is phosphorus or later, and they can violate the octet rule. So let's follow the standard method we've done though. So we started with single bonds. Now let's make sure everyone's fulfilling the octet rule. I wouldn't add any more bromine yet because it's already over 8. Let's get these fluorines taken care of. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Okay, now if we were to count up all these electrons in the picture, we're going to notice that we have, 2, 4, 6, 8, and we got 5 more. We got 5 of these. We got 40 electrons in this picture. That doesn't match, and it has to match. Now, this is not going to be adding double bonds, but this is going to be the opposite. If there are too few electrons in your picture, you need to add lone pairs to the central atom. Notice we're always adding stuff to the center atom, not the outside atoms. And we're never counting the lone pairs on the outer atoms, really. So let's just kind of fit it in there. We're going to jam 2 more electrons onto that central atom, bromine, and now we have 40 plus 2 is 42 total in the picture, and that matches. Now we're good. Let's do another kind of different one here. Xenon tetrafluoride. Now, we did say that noble gases don't like to react, but I would say that I guess there's exceptions to our little universe and some of our predictive patterns here. If you think about why this happens, it's kind of interesting. Think about fluorine's high electronegativity. And what happens here is fluorine wants to share electrons so badly that it can even convince kind of a noble gas to react here. Let's do the Lewis structure for this now. Xenon has 8 valence electrons. Fluorine 7 each times 4. So we're going to get here 7 times 4 plus 8. So we get 36. Let's get the xenon in the middle. Let's get the fluorines on 4 sides. Let's start with single bonds. Let's fulfill the octet rule. Now let's leave xenon alone for now. 2, 4, 6, 8. Let's fulfill the octet rule for my fluorines. 2, 4, 6, 8. And now we see that we have 2, 4, 6, 8. There's 4 of these, so that's going to be 32 electrons in our picture. So again, we have too few electrons in our picture. So I think we need to add lone pairs to the center, and we would have to actually add 2 lone pairs or 4 total electrons to that central atom to fulfill that octet rule. And where can you add them? I'd say just try and add them to 2 of these 4 corners, and then maybe space them out on opposite sides, not put them on adjacent ones. But at the end of the day, we're going to start translating all of these Lewis structures into shapes. And some of these questions about where should I draw it for now aren't going to affect what we do in the end. Okay, so I hope this helps, and we can now predict shapes based on these Lewis structures.